Hi everyone, welcome to this week 12 simulation analysis. Okay, for simulation is basically we draw data from a predefined formula and to do it repeatedly to get a random numbers and to form a multiple samples for analysis. Okay, so let's do a quick review. So here there is an example of a monthly wage of a working adult. So if we know that we have construct a mental formula, a mental model, the wage is 500, which is a base plus 600 times the year of education, then plus 300 of working experience. And this was saying that assume the year of education following normal distribution with average of 15 years of education to be received. And this n is the standard deviation or its variance. So it is a variance, okay? And the experience follows average 5 years of working experience and the variance is 1, okay? Then we repeatedly draw. Okay, so this is example, do it 100 times. So here is a procedure. So generate the first first wage. I draw the education from a normal distribution randomly and draw a work experience from the normal distribution for work experience. Then feed into this formula to calculate the wage, then save it. So this is your wage one, sample one. Then you repeat it for 100 times. So let's open this demo for week 12. Okay, so monthly wage, similar 100 wages, building a mental model. Okay, then making distribution assumptions. So yeah, distribution assumptions for education is 15.2. Then experience is normal distribution 5.1. Okay, so at the meantime, we do not set seed. If you want to set seed, you can we can always get the same set of numbers. So our norm n equal to 1, mean equal to 5, standard deviation is SQRT of 2. So this is the education, right? So if you repeat it, run it, you will see that we're drawing a average year of education. And second one is the experience, okay? Experience. Let's say we want to get 10, that's 10. So 10 or 1, okay? So this is the experience. And simulate and calculate. So I write code to generate many ID and calculate many wages be used as random sample. So this is not female I, it's actually EXPI. EXPI, okay, so EXPI file save as define a function to simulate the wage. So f wage function wage is a function, then wage is the exp. Oh, wait, REP is replicate 0 4 times of n. So if we want to simulate 100, draw 100 wages, then n will set into 100, so that give us 100. So the wage is 500, which is the base, plus 600 times the normal distribution that we want to get n numbers. So 100, n equal to 100. Then from a normal distribution of mean equal to 15, standard deviation as QRT2, then plus the working experience. So the working experience. Then we have already defined this function. So this is a function we already defined. Okay, function we have defined. Then after that, now we do is wage, f wage 100. So we can do this. Let's say we have 101. So it give us one value. Let's say so this one will assign to x. Then we display x. Each time you see that x value is shown here. So actually it changes. Okay. Each time it change, okay, so we draw 1. Let's say we want to draw 10, so each time with your x, you are seeing that x become 10, okay. Each time X become 10, if you change to 100, then it will create 100 wages. Okay, so that's the one that we're using. Then actual simulation, then let's view the histogram. So this is histogram, okay, for these 100 wages, okay. If you run it again, then you will see different histogram because we do not fix the seed value. So each time they will actually do some real random drawing. Okay, so my question is, what you are seeing here is widget sample, right? So these normal distribution, this is a normal distribution. Yeah, it may be the normal distribution. So the question here, what you are seeing here, this is the population distribution, sample distribution, or sample distribution. Okay, now the question here, the answer here is, this is the sample distribution. Okay, so this is a wage which is our sample. It is not the average wage. We're not drawing a few wages from this sample and calculate average. So actually this is an individual wage. So this is a sample distribution. Okay, run it, get the histogram, then mean value is this is the average value. Then we add a line to it. So this is the average. Okay, so each time when we're drawing different samples, the mean value will actually change. Okay, so it change from this number to this number. So each time we do simulation, then we may get different samples and the sample statistics. But if you want to fix the seed value, okay, let's set seed 42 and you run it, you always get this 10942, okay, or then we run from the beginning again. You always get this 10942. Okay, if you uncomment it, run the exact same code as mine, and when you have access to it, you will still get the same value that you see on the screen. Okay, so next is next example. Next is a dating problem. So Dan, Kelly, travel time. So Dan's travel time follows a gamma distribution with parameter these. And Kelly is following a different distribution, exponential distribution with parameter 10. Okay, so this is just for demo purpose. So next is we're going to calculate the difference in the travel time. So who is going to wait who? The person who actually takes longer time to travel will or takes shorter time to travel will be the person who are going to wait. So the waiting time is x1 minus x2, get absolute value. Okay, so this is what we're going to simulate. And here is the example. Okay, set seed 456, blah, blah, blah. This one, get a for loop to get a 10 data points. Then Kelly will get a draw from a exponential random number from exponential distribution, and I get n equal to 1. Then for Dan is from a gamma distribution and get a 1. Then calculate the waiting time. Then after that, repeat 10 times. Okay. Then calculate the mean value of the waiting time, calculate the standard deviation, then do a t-test to get the 95% confidence interval for the average waiting time. Yeah, average of these 10 waiting times. Okay, exercise now. Okay, so here is can get it. Okay, so do a histogram of getting 1,000 random numbers from a gamma distribution. This one is actually n equals to 1,000. So it's recommended you always write these parameters so you know which number is for what purpose. Okay, shape and rate. So each time you will run it, you will see slightly different 1,000 random numbers. So this is what is a gamma distribution about. So we have learned a few continuous random continuous distribution, which is got normal distribution. We have a uniform distribution. So this is another distribution, which is a gamma distribution. Okay, then for Kelly, the time follows is exponential distribution. Okay, exponential distribution. So we just draw an exponential distribution for Kelly. Okay, so these are the average waiting time from 0 to 0.6. and so on. Then this is exponential distribution. Okay, so the choice distribution is arbitrary for us. So basically just to show you that we can draw the simulation from various kind of distributions. Okay, so next we set seed, waiting time now is 10 0. So waiting time is there is initial variable hold 10 places, each of the place with initialized with 0 value, 0 hour. So write a for loop, generate 10 sample points, 1 to 10. Okay, so what we do is carry, we draw from n equal to 1, then rate equal to 10. Yeah, it's always good to write all the parameters, then shape and the rate, travel time in hours, then waiting time is absolute. Let's run it. Okay, after run this for loop, we have the waiting time. You see the waiting time is now updated. So now waiting time. If you run it again, you also notice the waiting time updated. Okay, then calculate the sample mean. So this is your waiting time. So let's have a look at your waiting time. Let's have a look at your waiting time. So this is your waiting time. Okay, so if you run it again, you will see different waiting times. But if you start to set seed, then run again, you will have a fixed shape. This is the shape that you're going to remember. Then we'll run it again, and it will give us the same set of random numbers. Then calculate the sample mean. The sample mean is h bar waiting time. H bar waiting time is 0.1, 0.1014. Okay, so that's the one. So run it again, you will still have this histogram of waiting time that you are seeing. Calculate the sample standard deviation. So waiting time. So this is your waiting time. Should look at this waiting time. Waiting time. This is a 10 waiting time. So we're going to calculate standard deviation. Why do we need to calculate standard deviation? Because we want to calculate the confidence interval. Okay. So one of the simplest way to calculate the confidence interval is to use a t-test. T-test. What use t-test, not z-test here? Because we do not know whether the population is normal, not normal, we do not know the standard deviation of the population distribution sigma, we do not know. So we are using a sample standard deviation to estimate the population standard deviation. Then we need to use t-distribution, okay? SW is 0.07, so never mind, we just use a t-test, supplying these 10 waiting times, and also the sample size is small, right? The sample size is small, and that's interesting. If you recall correctly, how many samples you have? You only have 10, right? So initially, if we follow the decision tree that I mentioned, you will actually end up into a bucket where you need more data. But if you are forced to calculate the confidence interval, then I remember I suggest to you to use t-test. So this is a scenario here. So sample size is actually quite small, only 10, but you can still use t-test. Okay, so this is your waiting time, t-test. Okay, t-test will by default give you a 95% confidence. Okay, it was 0.05 to 0.15 hours. Then you times 60, you are going to get the minutes. So about 3 to 9 minutes. Okay, 3 to 9 minutes. This is what you are seeing here. Oh, this t-test is giving you this value. Okay, let me run it again, see whether I'm going to get exactly the same value as shown here. Okay, waiting time, for loop, blah, blah, blah. Okay, the time for loop, let me try again. 0.05, 0.15. Yeah, I get this value. Mean value is 0.056, 0.05. Mine is slightly different. Potentially it can be the reason of R version. So sometimes when R upgrade a major version, then the random seed values may change. So this maybe one possible explanation that the slides result is different from the result from my R. But if you are using my R code to run in your own computer, you should have similar values as me. You should have the same value as me. Okay. So what if I want a, I'll say 95, I want it 90%, 90%. Let's say I want it 90% of confidence interval, the right confidence interval is 0.5. Okay, then you're going to get a 90% confidence interval. Okay, cool. So this is a review. Then the second example, next example is a simple investment problem. Also, this is investment. You're contemplating on investment scheme whereby you must make a 5,000 contribution at the beginning of it. So you read through it, blah, 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 blah. So read through it according to the video lecture. Okay, example 2. Okay, so your annual return follows a uniform distribution, minimum 3%, 3% loss, and 10% gain. So you simulate one for 1 year, you do it again. So you're going to see that that's the average return per year. We'll simulate this at the maturity date. Okay, so we created this total variable for us to store the random sample generated from the simulation. At the end of year 10, start of year 11. Okay, total value is 0, then total value of previous year. Okay, so I need these two variables here. And why not I just clear everything here? Clear everything. Let's start from fresh. So I see the total value and the total value of previous year. Okay. Then outer for loop is to generate 1,000 such investment. Sample size is 1,000. So we have 1,000. So it requires to generate 1,000. 1,000. Okay, yeah, it requires to generate 1,000. Basically, we are using this piece of code, okay, with some more explanations. 1,000. There's a loop to 1,000. There's an inner loop is to get 10 years. So 10 years. 10 years, one investment. Then we simulate 1,000 times. Okay, so you need to read this code to understand what is going on. So with the explanation here, right? Then your next year's value at the beginning of the year is last year's total value plus your contribution times 1 plus a return. 1 plus a return. Yeah, so in the beginning of the year is how much money you have. So let's run this for loop. After running this for loop, there's a lot exponent, debug information that I have inserted into it. It is showing that on the last sample, 1,000 sample, at the beginning of year 2, what is the total value? Because every year you get $5,000, right? But this one shows on year 2, you actually had a loss, because return rate can be -3 to plus 10%, right? So beginning of year 3, beginning of year 4, on average, every year you have about 5,000 top-ups. So 5,000, so it will increase. So this is at the beginning of year 11 or end of year 10. So this is the called total value for the 1,000th sample. And this is total value for the 999 sample, and this is the value for the 998 sample, and so on. So you have all of them, then you store them into the called total value. Okay. After that, you're going to look at total value. Total value, you have 1,000. Let's have a look at histogram of this total value. So this is a total value. Total value and the average of it. Average is 60863. Okay, then you add a line here. So you can do a quick calculation. What is the 10 years? Every year you have 5,000 times 10 years. This is about $50,000. So $50,000 is a total contribution, but every year you, on average, will have some profits in the form of return. So the average total values of these 1,000 simulations will give you $60,000 and above, right? So basically you are making a investment gain. Okay, so divide it, you see 1.21. Okay, give me one moment. This one is 5,000. So these two you divide by another times 10. In fact, it's just this one. Okay, 1.21. So on average, you are getting a 21% of compound profit after 10 years. Okay, so this is actually quite handsome, quite healthy return. It is pretty good return after 10 years overall. Okay. Okay, so that's the one. So next is we're going to generate 95% confidence of the mean. So what is the mean value? Mean value is already told you. So mean value is 60863. Then standard deviation. Standard deviation of these the total value. The total value. We're plotting this total value. Okay, so what is your standard deviation? So this is standard deviation of the sample, okay? So this is standard deviation of the sample. What are you seeing here? This is sample. So each of the 10 years return has been shown here. So that's a sample. So after that, we'll calculate the 95% confidence. So here we need to use the QTR. Okay. So lower limit is your average X bar minus this is your standard error, standard deviation of the sampling distribution. Okay. So here what you are seeing is the sample standard deviation divided by square root of n. Then you get a sampling distribution of the mean times the critical value, the t-score here. Okay, so this is your lower bound, upper bound. Then let's display it in total. Okay, so this is lower bound, higher bound, and the mean value. Actually, you can use a t-test as well. So total value, so just do it, total value, t-test. Okay, total value. Then you can also obtain the confidence interval immediately, which will be the same as your manual calculation using margin of error, and sample mean plus minus margin of error. So they are the same. Okay. So what I'm supplying here is the mu is, this is my H0 hypothesis, null hypothesis, which is what I'm saying that your actual profit gain is still the same as my contribution. So this is null hypothesis. Basically, I said what I want to the null hypothesis is your 10-year investment is useless at all. So it does not increase or decrease your principal, which is the $50,000 that you have contributed during the 10 years. I think it is the same. Then we run this t-test, then it's saying that the p-value is so small, right? Then it is significant, though we have sufficient evidence to reject the null hypothesis that investment is useless, you don't gain or lose anything. In fact, we need to accept the alternative hypothesis. So the true mean is not equal to $50,000. So you actually make a profit, and the confidence level of your actual the confidence interval for your total market value is at least 60,579, which is higher than 50,000. So the 50,000 is not within the confidence interval. It is in the two sides, which is in the rejection zone. So that's why we reject the null hypothesis. Okay. So next is analyze and compare total gains between year 11 and the previous year 10. So this is another thing. So length of total previous year, you also have 1,000. Okay. So basically that is the beginning of the year 10 of the previous year. Then okay, let's have a look. That is the sample distribution of the total investment value, total capital market value of the previous year. So which is the average is 553,000. And mean value then add a line. So it is here. So basically now we're doing two sample t-tests. And we're doing a paired one. The reason of paired one is among these 1,000 samples, for the first sample, you have the 11th years, which is a total total value and the total value of the previous year. So this is one pair. This belongs to the same sample. Then you move on to the second sample, right? The second sample, you have the total value and the total value of the previous year. So this is your total value, and this is your total value of the previous year. So total value have, let's look at the last row now. 1, 2, 3, 4, 5, 6. Then for the 995 total value, it has a corresponding previous year value is 5476. 54576. So they are one-to-one mapping. Okay. The 995's previous year will not match to the total value of another year. So it will always match to the 995. That's why it's called paired. So for this example, we're using a paired t-test. So you're noticing that p-value first is very small. So the null hypothesis is the current years the total value is same as the previous, so investment in use, but it says it's actually different. Okay, basically different. So the 95% confidence of the year sample estimate main difference is $7,000. So this is calculating the main difference. So the mean difference is at least $7,000 between the between the 10th year and the 9th year, end of 10th year and end of 9th year. So that's the confidence. So paired. So yeah, this is paired. Then we do a paired t-test. We say the 6 years, the end of 10th year's value is higher than is not higher than the previous year as a null hypothesis. Then alternative hypothesis is the true mean difference is greater than 0. That means the end of 10th year's total value is higher than end of 9th year's total value. As alternative hypothesis, which actually supports it's a one-sided paired t-test, alternative equal to rate. So these are all optional. So what I'm explaining here is two sample t-test and the paired two sample t-test and two-sided sample t-test and one-sided sample two sample t-test. Okay. So what it's saying here is your total value will be at least $7,055 more than the end of 9th year's total value at 95% confidence. Okay, so this is how you interpret it. Okay, so that's this called mini investment example. Okay, mini. So yeah, okay, this is the 95 confidence interval that is shown earlier. So this may be slightly different from what I've obtained earlier. So my 95% confidence interval is this 60578. So it's slightly different from this. total value. Okay, let me run it again. Let me run it again. Set seed, yeah, set seed from, oh, this is waiting time. Then after that, same example two, the slide did not mention um which random seed to you. It didn't mention. So yeah, so it's inevitably that our uh simulated confidence interval may be different. It says that we slide up to a few hundred. Yeah, a few hundred. Yeah. What if we do a set seed? Then we'll see how. Example two, let's say I do a set seed. One of my favorite number is 42. So let's run it. If you use set seed, then you will have a fixed confidence interval. Okay, so if you are using set seed 42, you should get the same value as mine. Okay, then optional things, then we run the optional things. Then you are seeing that the value may slightly change because we have drawn a different random sample using set seed random seed 42. Okay, so demo has ended. So that's the end of this demo. Then advantage and disadvantage. Okay, then that's it. So that's the slide. Okay, then we look at those tutorial for week 12. Okay, let's look at tutorial. If else statement, suppose x equal to this one, then how can you use if else statement to instruct R to print the sample mean is positive when the sample mean is indeed positive, and the print the sample mean is not positive otherwise. Okay, sample mean is positive, sample mean is negative. Okay. So now let's look at this R solution. Okay, R solution. The first one, okay, first one, mean value is positive. Okay, we set the X variable. Then we display the mean value 2.555. So it says if mean is greater than 0, then you have curly bracket, you say print. Else, then you print this. Okay, so run it. So the sample mean is positive. Run again. Sample mean is positive. If we have a negative 10 here, let's try this. Mean X are still small. So let's say minus 100, then it definitely will get a negative mean value. Okay, then we run it, they'll print the sample mean value is non-positive. Okay, so we will change it back to 10. Or we do this minus 100. Okay, minus 100, you have non-positive. Okay, so this one I comment first, later you can use. The second one is simulate a continuous uniform random variable from -1 to 1. So it's the minimum and maximum. Use the if else to print x if positive. Print x is all positive if it is true. Okay. Okay, uniform distribution. So x uniform, x uniform, x uniform, x uniform. We run it again, right? So if x uniform is greater than 0, print this. So this is 0.5. So it's positive. So let's say if it's negative, the chance that I'll get a negative, very rare chance to get negative because this one, oh, finally we have a -1. Okay, then we'll run it. It will print x is non-positive. Okay, non-positive. Okay, that's all. Following a yet y equal to 0 sample mean of x greater than sample median of x. Otherwise, y equal to 0. So compare mean of x and median of x with 3. So x is this histogram, mean value, median value. Okay. Then y is a value if this one is greater than this one, then what do? You assign 1, else you assign 0. Okay, so that's one way. to run it. Then you display y is 0 because your mean x is lesser than median x. Your mean x is lesser than median x. So basically here is for you to practice how to write if condition clauses. So this is something you need to practice. Okay, we can also check skewness. So we can use moments or the E1071, these two library. So the skewness function is contained there. So this is one of the example that I want to show you here is you are seeing that mean is smaller than median. In general, it will be left skewed. It will be left skewed when mean is lesser than median, left skewed. But when you actually calculate the skewness, it's positive. So that means it is right skewed. So it's not always true that the distribution is right skewed, and it will always show that the mean value greater than median, or if it's left skewed, it's always mean value lesser than median. Because this is sometimes sample size is small, then you may have a large movement of the median. Okay, so question two. Question two is a pretty complicated case. And you need to really master the question two, and you need to be able to solve a similar problem by writing the R code from scratch. Okay, so we'll walk through this question two together. Okay. So if you invest into a one portfolio with annual return estimate to follow the continuous uniform distribution between -3 to 7, which realized at the beginning of each year, the positive return in the form of a dividend will be reinvested. Okay. Assume you invest blah 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 at the beginning of the first year. Can you simulate one single instance of value of investment at the beginning of the 6th year? And set seed as 200. Okay, so this is pretty complicated. Let's do it one by one. So set seed 200. Let me clear everything here. Okay, set seed 200. Value equal to 0. Okay, contribution is 1,000. Then first year, second, third, fourth, fifth year. Okay, so we are not doing any other contribution at the beginning of the year. Similar one single instant of value in the investment at the beginning of the 6th year. Okay, 6th year. So this is your contribution. So for year in 1 to 5, so 5 years, return is a random number, minimum, maximum. So value year plus 1 equal to value year. Year is actually current 1. Value year 1 is 0. Then plus contribution times 1 plus return. So that's the year 2's return. Okay, year 2, which is realized at the beginning of each year. Okay, so let's run it. Then have a look at this value at the beginning of the year. Okay, at the beginning of the year. The beginning of the year is 0. Then you invest $1,000 on the second year. 1, 2, 3, 4, 5, 6, so on. The beginning of the second year, you are getting $1,000, which is your contribution plus the profit $23. Then you invest again. Then on the beginning of the third year, so you use 1.23.377 times 1 plus a random draw the return value. Okay, so that's the one. Okay, I think it may work to display this one. CAT. Why not we do a CAT? Let's say value year value, the year is value year, value year. Year of, then you want to display the year, value year. Also, you want to display the year. You do this value. Display the year. Year is your year, then value year is this value year. Then I want to also display the return. 1 plus return is 1 plus return. Okay, so let's return. Then dash slash n slash n. You need a backslash n to have a new line. Okay, let's run it. So I'm now seeing year one, value 0, return 1.05. Then the year two is $1,000 times 1.053. That's why you get this number, right? Then at the beginning of year three, is this, right? So 1.53, this one, you want to verify it, okay, verify it times this one. You want to see what it is value 1097, so same as 1097. So the calculation is correct. So when you're running this kind of simulation, make sure you have a few displays inside using CAD and make sure that you calculate correctly. Okay. Then let's see it again. Let's run it again. I need to run it again. Print value. Okay, so print value. So each time when you run the same thing, it should give you the same value. Let's run it again. We are seeing exactly the same one. 1166. Okay, 1166, 1166. Okay, which is okay. So we're done with that. So at the beginning of the 6th year, we'll get $1166.572. Okay. And the second one, build on one. Please simulate 100 instances of problem Q2.1. That is, we want to obtain one possible values of investment at the beginning of the 6th year. What is the average value of the investment out of this 100 iterations? Let's see, that's 200. Okay, so this is the backbone inside it. Now we're going to repeat it how many times? How many times? 100 times. Okay, 100 times. So now what we're doing is, so we have total value here, value here. Okay, let's clear everything. Total value numeric 100. So that means you need to hold 100 values. Each value is the total investment value at the beginning of year 6. Okay. So now loop it for 100 times. Inside it, I want to have a look at what is the simulation number now. So I want to look at what is the first sample, second sample, the third sample, right? Then the value will set to 0, so that the value that later we're going to store it. So here in 1 to 5, return is again in this range. Yeah, we should always have a good habit to have the parameter names. Yeah, always emphasize to have the parameter name. Then value 1 is value contribute. Now, so this line is, these few lines is what you have built in the previous places, right? So you have seen this. Then the total value of the sample size, so value 6. Basically, the value is, you print value 6, right? So this the value 6 that you have. In fact, the entire value you have is, okay, that one is missing now. The entire value is the 6 years investment value. Okay. Yeah. So now you get the 6 value of it, then save it into the total value sample size. Then you display the value at the beginning of year 6 is how much for the first sample. Then after that, total value here stores 100 simulated at the beginning of year 6, then histogram. Okay, so that's it. Now let's run this total value. Okay, so what you are seeing here, you have seen 100 simulations. The first part of simulation number is shown here. Then the second part is value at the beginning of year 6 is here. So they will concatenate together. They'll be showing one line. Okay, so first simulation, you get the average 11667.572, right? That's actually the one that we get when we're running the first, when we're running the question 2.1. Using C number 200. So it should be the same as the answer to question 2.1. Okay, then we repeat. Continue to do that. So make sure each of the number will be different as each of these simulation, they can't be the same one. Can't be the same one. Getting the same one, you have no variance at all, so it won't be correct. Okay, now this is total value. So total value at 100 total value. You plot the histogram. What you are seeing here is the what are you seeing here? Okay, so this is your sample distribution or sampling distribution of the investment on the 6 year. So this is sample distribution, not sampling distribution. Okay, sample distribution. So average value. So now you are calculating the average, print the average. Print the average is 1102. So this is 1x bar. Okay, 1x bar. 1x bar. 1x bar. Average return of this 100 simulated year 6 total value. So a sample size is actually 100, so another 1100. Okay, so question 3. Now suppose you invest 1000 at the beginning of each year of the next 5 years. Can you simulate one single instance of value of the investment at the beginning of 6 years? Set the seed as 200. Okay, so this is the extension here. So now the contribution or the difference here is the contribution has changed. Earlier, your contribution is this, right? Earlier, your contribution is this. Okay, you only control on the first year, then the rest of the 4 years you don't contribute. But now your contribution actually changed. Your contribution become not 1000,000. So you run this line, you have 1000, 1000, 1000. So you invest every year. Okay, so let's run assess seed, initialize this contribution. Then after that, in year 1 to 5, you draw from random, you draw from normal distribution, you draw from the uniform distribution of your return. Then you calculate the 6 year beginning, okay, value at the beginning. Okay, run it. So what we are seeing here is at the beginning of year 2, because year 1 you invest how much? At the beginning of the year 1 is 0. So at the beginning of year 2, your new contribution at the beginning of year 1 is 1000. So 1 plus return is this, then current total value at the beginning of year 2 is this amount. Okay, then move on to year 3. value at the beginning of year 2 is inherited from the previous iteration, then 1023. Then new contribution at the beginning of year 2 is $1,000. So now at the beginning of year 3, so at 1 year passed from year 2, then you can calculate the new return, and at the current time at the beginning of year 3, you should have this 1,000 plus 1,023. Then you have $2,023 times 1.0283, you will get 2,080. Okay, so this is how you calculate at the beginning of year 3. Then you continue to do this for year 4, year 5, and at the beginning of year 6. The value at the beginning of year 5 is this amount, and plus this year's new contribution 1,000. So you have 5,333. 5,333 at the beginning of year 5. Then at the beginning of year 6, 1 year pass, you have an additional 3% profit. Then use the 5,333 times this return, you will get 5,528 at the beginning of year 6. So basically this is what it is saying. Then you are showing the value, then for at the beginning of each year, year 1, year 2, 3, 4, 5, 6. These are them. Then you print the last one. This is the last one. So we have solved this question 3. Then next, and now suppose you are investing $1,000, $2,000, $3,000, $4,000, $5,000 respectively at the beginning of each year for the next 5 years. Can you simulate one single instance of the investment at the beginning of the 6th year? Okay, instead of 1,000 at the beginning, now you have to change to this. So question 4. So now the only difference is your contribution change. Okay, so contribution 1,000, 2,000, 3,000, 4,000. All the rest of the code is the same as the previous one. We just change the contribution. The contribution changes. Here is the contribution. So it actually will extract the contribution based on year. So you can try this. Contribution 1 is 1,000. Contribution 2, contribution 3, contribution 1, contribution 2, contribution 3, contribution 5. You get 5,000. Contribution 6, you can't find it. Okay, so basically this is what you can get. This is the code will get a different contribution for each of the year. Okay. Okay, so I leave it there. Okay, so contribution. Then after that, for year in 1 to 5, again, you are seeing these, right? At the beginning of year 2, you have invest 1,000. At the beginning of year 1, beginning of year 2, you invest additional 2,000. Beginning of year 3, you invest 3,000. So every year you actually invest more. So by the beginning of next year, you use 4,000 plus 6,000 plus, then times this percentage, then you will get these. So we can do a quick verification. So for year 5, okay. So we do for year 6, okay. Year 6, we copy this one. We can do a quick verification. This one plus 5,000. This is the money that you have, then times this value 1 plus return. Is it equal to this value? Double. We expect to get a true false. Why it is false? Okay, let's try again. Let's have a look at what is the actual value of this. 162.64.59. Okay, 162. Yeah, so it looks the same, but if it's wrong, there is some minute invisible numerical difference in our software engine, but in general, these two are the same. Okay, so these two should be the same. Yeah, these two should be the same. Okay. Okay, now look at this 6 years investment gain, and the last year is 1,626. $64.59. Okay. And next is we're going to 5. Okay, so things are getting more and more complicated. Okay. You invest $1,000 at the beginning of the next 5 years. Now your bank gives you a new deal. If the dividend for a year is positive, instead of revisiting it, the dividend will be withdrawn immediately and be used to purchase NTUC vouchers. Calculate the average vouchers from 1,000 simulation runs of the total value of the investment and the total value of the voucher obtained at the beginning of the 6th policy. Okay. Okay, so I see the 200. Calculate the average value of 1,000 simulation runs of the total value of the investment at the beginning of the 6th policy year. So if you get a profit, right, instead of reinvest, the profit will be converted into basic cash into another account to buy the NTUC voucher. So you want to find that money if it's positive for each of the year, then sum them together, you will get that entire total NTUC vouchers at the beginning of the 6 years. So this is 5. So 5. So 5 says the total policy value and total voucher. Total policy value is the original total value that you have. Then the voucher is if it's positive, you get voucher. If it's negative, then you don't get that voucher. Okay. Okay, we try 100 samples. Okay, 100 samples. Then cat simulation number. What we did is contribution. You do $1,000 for the continuous 5 years. Then extract the total policy value or your investment, your principal value at the beginning of the 6th year and the total vouchers. Okay. And now it start to run it, then there's your return, then policy year plus contribution year is your voucher times return. So if your return is greater than 0, if that year's return is greater than 0, then you are getting some vouchers. The voucher is the total value that you are having, and this year's contribution then times the return. So this is your total voucher. Then the policy year is the policy year from the previous year plus your contribution. Okay. So if the return is not positive, that means your voucher definitely is 0 for this year. Then your policy, your return is actually 0, right? So your policy plus your contribution times a discount. Basically, you're losing money. So your new policy year plus 1 will be will be this new value. And after that, policy year equals a policy voucher. So now you sum the policy voucher. Policy voucher is a current voucher that you accumulate with sum all the previous years policy voucher. The voucher at the beginning of the year, policy voucher. Okay, so let's just run it. Okay, we run it. Then at the end of it, you can have the total of policy value. So this is pretty complicated. So you need to build it one by one with a few debugs. Okay. So now these are the results you are seeing. Okay. We are simulating for how many? 100. Okay, we are doing 100. Okay, we are doing 100. So what you are seeing here is this is simulation number 100. Okay, we actually simulate 100 times. This is 100s. So 100s, we have 5 years. Okay, at the beginning of the year 2, okay, what is the policy value and the voucher value are 0, and new contribution of the year to 1,000. Then for that year with a random seed 200, your return is positive. Okay, so first your return is positive. That means you are going to earn voucher. So your new voucher purchase is 1,000 times this value. So you have $6 voucher in NTUC $6 voucher, and the current total policy value will be 1,000 because you only received that money. Then you move on to the next year. So policy value at the beginning of year 2 is 1,000. Inherited voucher is $6. So new contribution at year 2 is another $1,000. So you are just investing, continuously invest $1,000. Then after that, you calculate the return. Okay, the return is positive. That means you can still earn earn voucher. Okay, so new voucher purchased. How do you calculate this new voucher purchased? The new voucher purchased is about 5% times how much money you have. You have 1,000 plus 1,000, $2,000. Okay, $2,000. You have this $2,000 times this one. Then minus $2,000 because you only invested, you only obtained the voucher for the surplus. Okay. So 106. Okay, so this is a NTUC voucher that you earned for this year at the beginning of the year 3. Then you sum it to the previous $6. Then you get about $112 in voucher, and your current total policy is $2,000 because you have accumulated 2 years, 1,000 to $2,000. Basically, if you gain a profit, then you park the money into a different account. Basically, it's pay interest, and the interest is not going to be reinvested or accrued into a principal. So at the beginning of year 4, you're still earning money. Okay, you do the same thing. You're still earning money. Still earning money. Earning money. All earning money. Okay. So this is example that is showing that your total currency product in the entire 5 years you never lose money. So return is always positive. So by end of year 5 or beginning of year 6, you have your principal of $5,000. You invest $1,000 per year for the over 5 years, and the total voucher accumulated is this. So this is 100. Let's find one example that you have a negative return. Okay, so let's have negative return. So here is one negative return. Okay, let's look at simulation 99. Okay, so you're a bit unlucky on 1 year, actually the first year that you are incurring a loss. Okay, so your voucher will be 0. So when you're incurring loss, you are not gaining any profit. You are not able to receive an NTUC voucher, and your principal actually gets reduced, shrink. So from 1,000 to 900 plus. So then on the year 3, your return gets positive again. So now new contribution left here is 1,000. So 1,000 plus 997 is your new market value principles. Then you times this 0.023, you get a $47 surplus to buy a NTUC voucher. Okay, that's the one that you have, and currently your principal is 1,000 plus the 997, so you get this total policy value at the moment. Okay, and the voucher is this. Then you go to year 4. Year 4 is you have this 1,997 plus this 1,000, and again you are incurring a loss. So when you're incurring a loss, that means you do not have a profit. Do not have profit, and the new voucher will be 0. 0 plus 47, you still have 47 for this year, and the total amount is 2,997. Need to get a discount about 3%, so you get a 2,915, which is lesser than your 2,997. Okay, so you are again incur a loss. Then go to year 5, and you're better. You have some profit again. So 2,915 plus 1,000, 3,915 times 3% is about $132 voucher, and at the meantime, your total principal is 3915. Okay, 3915. Then we'll go to year 6. Then again, you're positive. So you are going to have more voucher for this year, and this voucher 209 plus 180, you get $398 voucher at the beginning of year 6. And then the total principal of policy is 3915 plus that year 5's contribution of $1,000. So this is the end result for your 999 sample. Okay. Okay, so basically you have already contained all of them. So now let's have a look at the total policy. You have 100 total policies, and you have 100 total vouchers. 100 total vouchers. Okay, 100 policy and 100 total vouchers. So have a look at the total policy again. You see many of the 5,000, 5,000, 5,000, 5,000. So when you're seeing 5,000, what does it mean? It means over the 5 years investment, if you see $5,000, that means none of the year actually lose money. Every year the return is positive. That's the reason that you can achieve $5,000. You never lose money. Okay. Okay, if it's not $5,000, you know, at least 1 year in that sample, the return is negative. Return is a negative number. Okay. So now let's plot this histogram. So this is to set the plot into 2 sides. So one row and 2 columns. So basically split this area. Okay. So histogram for total, that split into here. Then main line. So let's just show it. Okay. So this at the beginning of year 6. So what we are seeing here is how many data points are here? Do you know? How many data points are there to form this histogram? We have done 100 simulations, 100 simulations. We have done 100 simulations. So there's 100 data points. So each of the data points is the year 6 policy value. Okay, the majority is $5,000. That means you never lose money. Some of them you lose more money. Okay. Then a total voucher value at the beginning of year 6, right? So the mean value is 362. 362. So on average, you will over these 5 years, you'll get about $362 of voucher. And this is more like normally distributed. Okay, the earlier the mean is about 4,937. So on average, you lose a little bit of money, but you actually earn profit in the form of NTUC voucher or a cash. So this is what you are observing. Okay, so next is below numbers are sufficient for completing the quiz. So average policy value, average voucher print. Okay. So this is your average policy value, and this is the average voucher that you obtain. Okay, so these are the 2 values that earlier we have seen. Average and average. Okay. Average. 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 Okay. So we say, what is the total value of the voucher obtained at the beginning? Calculate the average from this 1,000 rand of the total value of the investment and the total value of vouchers obtained. So that's the one. So that's the average. Okay. These 2 are the average. Average policy values and average vouchers that you have earned, which is average of 100 data points. Calculate 95% confidence. Before we move to that, I think earlier I mentioned is instead of using 100, also try many samples. So add a few more, 0, 0. Okay, so I have a lot. Okay, that will run it. run it. Wow, this will run slightly longer because we are going to run 10,000 times. So this runs pretty long. So you have 10,000. Now you have 10,000. So 10,000 values, 10,000 values. Yeah, then we plot the histogram. Basically, I want to show you this histogram. So average and average, then let's explore. So now you're seeing, so what you're seeing is these two distribution doesn't seem to be normally distributed, especially the right side. So this is not, it's exponential distribution. And for the right side, this doesn't seem to be a normally distributed one. So you have a longer tail in the right. Okay, so this is telling you that yeah, these sample distributions might not be normally distributed. Okay, these are sample distribution. Each of the data point here is the simulated year 6 voucher or year 6 policy value at the beginning of the year 6. Okay, and we only have two mean values on average of the total policy of beginning of year 6 and the one in of voucher value. Okay, so larger ones shows better better distribution. Okay, now we need to move it back. Remove two zeros and run again. Or the set seed, then run again, run again, run again, run again, run again, run again. So average and yeah, two averages is correct. So calculate 95 confidence interval for the total voucher value for 5. Total voucher value. Okay. Total voucher value is this one. So this is your total voucher value. So these are okay. And this is the histogram actually showing here. So this is a voucher. This is a voucher. Then do a t-test, confidence interval 95. Yeah, so this is the one. Right. So you get this. Okay. I also write this confidence interval, then display the confidence interval. Okay, same thing. Okay, what if you want to calculate manually using this formula? You want to calculate manually using x bar plus minus margin of error. Okay, let's use this one. So x bar, how do you calculate x bar? This is your x bar. This is a x bar. Okay, x bar. Yeah, x bar. Then margin of error, or how do you calculate margin of error? ME equal to CV times SE. CV is Q naught or QT. QT. Okay, probability is 95% confidence, 0.975, 0.975. Degree of freedom. What is the sample size? The sample size is length of total voucher. So we can LENGTH. Length of total voucher is 100. So it's a make it more systematic. We say this one minus one. Okay. So now your critical value is 1.98 because the sample size is pretty large. It's 100. So the critical value of t distribution is very similar to the z distribution, which is 1.96. So 1.9 and 1.96 is similar. So after that, your standard error. Now, what is your standard error? This is your CV, right? This is your CV. And standard error. Standard error, we do not know the population sigma. We only know the standard deviation of this variant, this sample. So standard deviation of this sample is 1, right? Divided by SQRT square root of the sample size, which the length of it. So basically it's actually 100. So just don't use 100. Just write this 16. This is your SC. Okay, this is your SC. So next is ME is this one times this one. Right, so it's best we add a bracket there. This is your ME. You just run it. So ME is 33. Okay, so this is your ME. Why now we do this? I will say this is ME. Just assign it to this value. Okay, ME assigned to this value. So now you have an ME. You have X bar. X bar is this mean value. So mean value plus ME and minus ME. Minus ME. So it is the same as your t-test value. Let's have a look here, t-confidence. Yeah, 329.387, which is your lower bound, which is the same as you're using t-test, and your upper bound is also the same as it. So if you manually calculate, you get the same thing, okay? So this is the CI upper limit. This is the CI lower limit, right? Okay. If I'm not wrong, we can also write on this plus b minus 1 plus 1 times maybe try this. Okay, yeah, same, yeah. So this is your CI. Okay, so this is manually calculated. Same as you are using the t-test. So t-test will give you this range, then manual calculation will give you the same range. Okay, same range. Okay, good. So it's called manual CI calculation. Okay, calculation. X bar plus minus M. This is your X bar. Sample me. This is your and sample size. Okay, cool. Okay, now let's move on to the last one. Okay, last one. A juice store in the canteen starts its business every morning with 50 liters of juice with no possibility of replenishment during the day. The owner expects to sell X liter during every business hour, where X follow a uniform distribution between 3 and 5. Suppose the store is open for 10 hours per day. Evaluate the sample milliliters of the unsold juice at the end of the business day based on sample size of 1,000. Set seed into 200. So basically, we are going to draw a sample of 1,000, and every day you operate 10 hours, and each hour you can sell 3 to 5 liter of juice. So maximum you can sell 5 for continuous 10 hours. 5 times 10 is 50. You just sold everything, okay? So no surplus, no unsold juice. So set C, the total unsold for 1,000 days. Total unsold you see on 1,000 zeros. So now for sample size in 1 to 1,000, loop over 1,000 business days. So we're going to see for each of the business days how much we are unsold. Okay, so X follow a normal distribution, generate 10 random hourly demands. uniform distribution between, okay. So every hour, basically how many liter you sell. Then 10 random hourly demands in liter is actually seeing 10 numbers. Total demand, you sum into it, and total unsold for the first sample is max 0 of 15 minus some x. So 15 minus some x is, if you have unsold, you will have some value is not 0, then your max function, you will get that value. Okay, then you display it. So this is what is being done. Okay, so run it. Okay, so I have iterated 1,000 times, 1,000 times. In fact, I would recommend you was actually start from small one, even from 5. Let's say 5, let's do 5 uh 5 simulations. So let's do from side 5. You should start from 5 first before you scale up. So 10 random hour demands is, these are the 10 numbers. So total demand, you sum them together. Total unsold is 50 minus that value. Okay. Total unsold. Yeah, every day on average, you will have some unsold ones. It's rarely you have sold everything. Okay. So now it scale up to 1,000. 1,000. Okay, now we have to set seed again. Run the set seed again. So this is 1,000. Okay, then you do a histogram. You draw a histogram. Okay, so average daily unsold juice is 9.97, about 10. About 10. Okay, so that's the one. So the mean value of unsold is this value, then displayed is 9.974903 liters. If you are asked to round into 4 decimal points, then you retain 4 decimal places. Okay. And the second one is, yeah, the owner adjusted his prediction of X to be normal distribution of mean 45 or 4.5 and standard deviation 1.5. Estimate number of days in which the store will stock out in 100 business days, set the seed value to 200. Estimate number of days in which the store will stock out. Basically, they sold everything out of these 100 business days. Not enough stocks to sell customer. That means the demand is higher than the supply of 50 greater than 50 not greater equal. Greater equal, less or equal means just nice, right? So the last customer just request for the exact amount of the remaining juice in that store. Then after that, your store closed. Then it's not considered as stock out. Stock out is only when customer come before business end, then they want some more which you do not have. Okay, they want some more amount which more than what you have. Then that's a stock out. Okay. Okay, now next is question 2. Says C, the total consumption is 0, days stock out is 0. So out of these 100 days, X generate 10 random numbers. Okay, again, yeah, it's best to have a 10 random number mean value, standard deviation 1.5. So I think it's best to add here as well. And minimum 3, maximum 5. So that'll be easier for you. Okay, so now next is just run this for loop. So let's run this for loop. Okay, so let's have a look. 100 days, total demand in the little greater is a stock day. 51 greater than 50 is a stock out. So you have a larger demand more than 50, then that day 100 is a stock out. Then day 99 is not, day 98 is not. It is only a stock out day when your demand is higher than 50. Okay, so now let's print it. The number of stock out days in a normal distribution is 13 days. Okay, so how do you calculate 13 days? Stock out days. Stock out days is actually being calculated here. Okay, so that's a stock out day. Okay. Now it's just being displayed. Okay, so if the sum x greater than 50, then you have a counter to increase it. So in the end, you have 13 days. Okay, 13 days. So optional locate. daily juice consumption, total juice consumption. And let's look at, so this is daily juice consumption in liters. Then add the average. Okay, average. Then total consumption greater than 50 is 30. So what is the average? Let's display what is the average value. The average is 45.23. So on average, 45.23 liter of juice was sold, and the remaining unsold juice about 5 liter. Okay, about 5 liter. Okay, so that's the end of this week's content. Yeah, thank you very much.